start recording. Okay, so I see the screen somehow flickering, so I don't know if you see that or you see it normally. But anyway, let's proceed. Okay, so let me first of all ask you the following: please, whenever you have a question, feel free to interrupt me and ask question verbally or in the chat. Second, if you see me making a mistake, sometimes I make mistakes, and please correct me. So either in the chat or verbally. Last time I realized that when I was speaking, instead of saying the positive charge repels positive charge, I said it attracts. So correct me when you hear or you see a mistake in my slides. Okay, so let me quickly go over what we have seen last time. Okay, so first of all, we introduced the experiment that was done by Benjamin Franklin. That's where he found out about the glass being positively charged when it's rubbed, and positive charges repel each other, negative charges repel each other, but when you have a positive and negative charge on a glass rod and on a plastic rod, they will attract each other. He called one positive and one negative, and that's the convention we are using. Usually objects are neutral, but they can be charged, and by rubbing, for example, if you rub silk and glass, you can have the silk negatively charged and the glass positively charged. And we've seen how we can use the triboelectric diagram in order to determine which material gets positive charge and which material gets negative charge. So positive charge repels positive charge. Forces are opposite in direction and equal in magnitude. Same thing for negative charges, but the opposite charges will attract each other with forces of equal magnitude and opposite direction. Then we mentioned the concept of conservation of charge. We said if you have a system isolated, that means there is no external charges coming in or going out, then the charge is conserved. The change in the charge is equal to 0, or you can say the charge is constant. So if you rub two materials against each other, you just have the negative charges that accumulate on one material and the positive charge on the other material. They will actually cancel each other. Okay, so that is the concept of conservation of charge, and we use this in an example of two balls, two charged spheres, and we've seen how, and we did an example where we verified this. Okay, I also described briefly the Robert Millikan experiment, and that he got the Nobel Prize for, in which he determined that also charge is quantized, meaning the charge is always a multiple of the elementary charge E. It can be positive or negative, but it is an integer number multiple of the charge E. It cannot be a fraction of E. Okay, I defined the current for the purpose of understanding. I is the current is the dq dt, or the amount of charge flowing per unit time, because the unit of charge is coulomb, and 1 ampere, which is a unit of the current, is equal 1 coulomb per second. Okay, we indicated how we use the symbol for materials, and we said we use atomic mass number as a superscript, and which is the number of protons plus the number of protons, and the subscript before the letter is the number of protons, or the atomic number. Okay, all right, we mentioned that in conductors, and when we have a conductor like a metal, we have free electrons that can move. These are valence band electrons. They can be free to move, and that's why we call it a conductor. However, insulators like glass and plastics, the electrons are not free to move. They are tightly bound to their atoms and molecules. Okay, and we had an interesting question. I forgot to ask the question. Was, well, if the electrons are tightly bound to the molecule or to the atom in the insulator, how come we can charge them? And I promised that will be the next slide that we will cover. So let me go into this slide and start the presentation mode. Okay, so we're going to be speaking how we can charge an insulator when we by rubbing. Okay, so this is so let's assume you take a plastic and wool and you rub them against each other. Okay, and we said you end up with the plastic being negatively charged and the wool being positively charged. So how does it happen if the plastic does not have free electrons? Well, so this diagram explains what really happens. Okay, so let's assume you have a molecule in the insulator. Okay, and the molecule has a number of atoms depending on the material, and there is a bond between these atoms. So when you do rubbing, the friction causes the molecules or some of the bonds in the molecule to break, and you end up, let's assume, for example, in this case, the molecule breaks into two molecules. And what happens is when you break the bond, the electron might go to the right side, and you have one extra electrons on this side here, okay, and hence one less electron on the side. So you end up with part of the molecule negatively charged and part of the molecule positively charged. Okay, so what happens in the glass rod? So in this case, the molecules that are breaking, the molecule that is on the glass rod has one or more negative charges, and the wool will have the opposite or positively charged. But if you add the electrons here, the negative charges and the positive charges here, they should cancel each other from the principle of conservation of charge. Okay, so the interesting thing is when you charge the insulator, the negative charges do not move, because we said an insulator, there is no free electrons to move. So these are actually molecules or part of molecules that are negatively charged. So this negative charge is not free to move. And that's why when you charge an insulator, the charge will remain restricted to the area that you rubbed. They will not move around. Okay, unlike a conductor, when you charge the conductor has free electrons and they will be able to move around. Okay, so I hope this is clear. I forgot to ask the question yesterday. Is this clear? Okay, is this, yeah, okay. Who asked the question? Is it Lanud? I forgot. Okay. Well, no, the atoms cannot move. So they cannot move. These atoms are part of the structure of the insulator. They cannot move around. So you can have, it's not a liquid. In a liquid, you can have molecules moving around, but in solids, the molecules are fixed in place. But in solids, it depends whether it's a conductor. If it's a conductor, the valence electrons on the atoms are free to move. Not all of them, but some of them are free to move. Okay, but in the insulator, they are the electrons are tightly bound, and they cannot move in the insulator. Okay, so this is how we can induce negative or positive charge on the insulator. Okay. All right, so let's move to charging a conductor. Okay, there are actually different ways of charging a conductor. Okay, so what you can do, you can, for example, charge a plastic, which is an insulator. For example, let's assume this is a plastic here that is negatively charged. Okay, and when you okay, so here yes, and when you touch the metal, okay, yeah, this is now interesting. Okay, so we said okay, so normally, yeah, this is not easy to explain. Now, if these negative charges are fixed in the molecules, how can they transfer to the metal? Okay, so if it was a positive charge, that is much easier to explain, because when you have positive charges, you have electrons and that are free to move in the conductor, they will move here. Okay, now what is difficult to explain is if this is now negatively charged, and if you touch the metal, normally the negative charges are not free to move, and here we don't have free positive charges. The metal has only free negative charges. The positive charges are protons. They are they are fixed to the atoms. Okay, so well, we'll see an example, but this is something that one have to investigate. But let's assume, so the negative charges somehow can be transferred, and we end up with the metal having more negative charge. Okay, so when you have the negative charges, when they accumulate on the metal, they will actually distribute uniformly, so they will be spaced in such a way the spaces are almost equal, so they will distribute uniformly on the surface of the metal. We will see this in a future lecture. In electronic equilibrium, all the extra charges on a metal or on a conductor will go to the surface of the conductor. Inside the conductor, there will be no net charge, but the extra charge will always accumulate on the outside of the conductor. So let's see. So the metals or the conductors, they can be charged by touching. So if you have an object that is charged, especially if it's positive charge, when you touch it, the free electrons will move to the charged object, the negatively charged object, and they will leave behind a positive charge, and vice versa. Okay, so in an isolated conductor, any excess charge is located on the surface of the conductor. In electrostatic equilibrium, we will see this in the future lecture. Okay, so we can charge conductors by contact, but also let me show you this illustration here, or this demonstration. So let me copy the link. Copy link, and we go to H. Paste. All right. Okay, I'd like to show you something besides contact. The metals can be charged by induction. So let me run this one.
Scope works, and to have you a bit of an understanding of how conservation of charge plays a part in how it works. So what I have here is a perspex rod and a piece of silk. And a perspex rod and a piece of silk, when in contact with each other, will cause some electrons to be transferred from one substance to the other. Namely, some electrons are...
Okay, so here, a correction, as we explained, so the perspex is an insulator, like a glass, and so it's not really electrons being transferred, but the molecules are left behind with positive charge, with net positive charge, and the silk will end up with a negative charge. All right,
are taken from the perspex onto the silk. And if I were to rub it a little bit more vigorously, I would cause more electrons to be transferred from the perspex onto the silk. We have conservation of charge. We haven't lost any electrons. They've just been transferred from the perspex onto the rod. But how do I know this is positively charged? Well, that's just where the electroscope comes into play. So if I rub this like so, and then place it over the electroscope, you can see the needle starts to move away. If I take the perspex rod away, what happens, of course, is the needle returns back to normal. But why is this so? Well, when I bring this perspex rod close to the metal plate, and this is connected here with metal connections over here, is that as I bring the perspex rod close to this, the electrons in the metal, they are conductors, will start to be attracted towards the top of the plate. In other words, if I bring this closely like this, the top of the plate becomes slightly negative as the electrons are attracted to the positive perspex up here. Of course, now that means I have slightly less electrons down the bottom, and I have two bits of metal, one that is balanced very sensitively and one that is fixed. And what happens, of course, is both become slightly positively charged. Because they're both slightly positively charged, they will repel. But as soon as I take the rod away, of course, the electrons that were attracted to the top of the plate now return back to their original position. They spread out evenly over the metal, and of course, it returns back to normal. But what if I want to have this needle stay fixed? Well, one way I can do that is I can touch this with this perspex rod. Why? Let's see how that works. Charge it up, I bring it close, it deflects, I now touch it and just make some contact like so, and then move it away, and it stays in the repel position. What I've done is I've actually removed some electrons from the electroscope, and they've moved onto the positive charged perspex rod over here. And now, of course, this is overall get a slightly positive charge, and the two pieces of metal stay repelled. What if I touch it? Well, my body is connected to the ground, and of course, if I touch it, some electrons from the ground through my body will neutralize this, and so we will get our electrons back. I touch this, and the needle returns back to normal. And so now I've demonstrated.
Okay, very nice illustration. So here we've seen actually three concepts explained here. Okay, so let me go back to the presentation. Okay. Escape. All right, so let me go here. All right, so we have seen two things. Okay, first of all, he illustrated with the electroscope how we can induce a charge redistribution in the conductor. So when he brought, okay. So when he brought the positively charged perspex to the electroscope, okay, the negative charges, the free negative charges were attracted to the top, okay? And so this left a positive charge on the needle. So this is a positive charge and a positive charge on the fixed bar here. So positive charge, and they repelled each other because these are connected, okay? So here we are inducing charge redistribution by induction. So here we are charging, this is temporarily charging by induction. Okay, as soon as we remove the perspex away, the negative charges, they go back, and the needles, we have neutral charge, and the needle goes back to its original position because there is no repulsion. Okay, so this is the first thing that he illustrated. The second thing he illustrated is that when he touches the perspex, so this is positive charges, and when he touches the electroscope, the negative charges are transferred to the they are attracted to the perspex because it's positively charged, and they leave behind a positive charge on the bar and a positive charge on the needle, and they will repel each other. Okay, so in this case, so he touched it, then he removed this, and we ended up with a positive charge remaining, a net positive charge remaining on the electroscope, on the metal. So this is now charging by touching. Okay, so charge by induction, charge by touching. The last thing he illustrated is the grounding. Okay, so the electroscope had a net positive charge. Okay, so this is the needle, had a positive charge. When he touched the body of the human body, okay, so here the human body is connected to the ground. Okay, what happened is electrons flew from the ground through the human body to the electroscope, and they neutralized the positive charges. So we ended up with neutral charge. So when you do that, you have seen the needle went back to its original position, meaning the negative charge moved onto back on the electroscope and made it neutral. So this is a concept of grounding. Okay, because Earth is, you can say, it's a big container of charge. Okay, and so if you connect anything to the ground, if it has extra negative charges, they will flow to ground. So if you have a metal that has a negative charge and you connect it to ground, the extra negative charge will flow to ground. And the opposite happens. If you have a metal that have positive charge and you connect it to ground, the electrons will flow from the ground to the metal and they will neutralize it. Okay, so this is a very nice illustration of the electroscope, and this will allow us to proceed with our discussion. Okay, so let me go back to the presentation mode. Okay, I did not stop to ask. Anybody has a question? Anybody has a question? Okay, all right. Okay, thank you. Again, remember, you can always speak in the microphone if you have a question. Okay, so also you can, if you perform an experiment, let's assume you have a neutral conductor. This is a neutral conductor here, and let's say it's copper, and you attach to a non-conducting thread, for example, made of plastic or whatever. Okay, and if you charge a glass by rubbing, and you charge it with a positive charge, we notice when you bring the positively charged glass close to the conductor, it will cause it to be attracted to it. So there will be an attraction. Okay, so same thing if you take the glass rod to the other side, it will also attract the other side. So in both cases, it will attract the conductor. Okay, now my question to you is, what do you think is happening? Why there is an attraction? So you can either turn on your microphone or in the chat you can give me the answer. Why do you think the rod is attracted, the metal rod is attracted to the positively charged glass?
Because the electrons are attracted to the positive, so they are at the since it's a conductor, the electrons move in the conductor freely, yes. And then they go to the end.
Yes, thank you, Salama. This is correct. Okay, so here what we are having, we said a conductor has a free electrons. Okay, so originally the conductor was neutral. Okay, but when you bring the positive charge close to it, the positive charges will attract the free electrons, so they will accumulate here and leaving behind positively charged atoms or molecules here, and this will cause the attraction between the glass rod and between the metal rod. Okay, so basically it's charge redistribution because the free electrons are attracted to the positive charge, and that's why we have the attraction. Okay, all right, so this is what we started with, a neutral conductor where the negative charges and the positive charges were distributed uniformly in this conductor, and there was no net charge. Okay, and still when you bring an insulator, the total net charge on the conductor did not change, except we have a redistribution. The free electrons have moved to one side. They were attracted by the positive charges on the glass rod, and that causes the force of attraction. Okay, so we can say in this case we have a charge redistribution by induction. So the higher electron density induced negative net charge on the left side, leaving the right side positively charged. So this is a charge not by touching, it's by induction. There was no touching, and we have only a charge redistribution. As soon as we remove the glass rod away, the electrons will go back to, and we end up back to a neutral situation. The uniform redistribution of electrons in the conductor. Okay, so but notice here the net charge on the conductor is 0, and also the net charge here is 0. Okay, so we have only charge redistribution. We don't have addition of positive or negative charges on the conductor because there was no touching. Okay, so this is the explanation of what I just mentioned. Now here we are re-explaining grounding. Okay, so charging a conductor by induction and removing some negative charge by grounding. So what we can do, let's assume we start with a sphere that is neutral. It's a conducting sphere, but the positive and negative charges are uniformly distributed, so there is no net negative charge or positive charge. Now, let's assume we bring an insulator close to it that is negatively charged, okay, and the insulator does not touch the sphere. So now what you have, the free electrons, they will move away from the negative charge, the insulator. So the electrons now are moving to the right side, leaving behind positively charged. This side is a net positive charge on the left side, and we have a net negative charge on the right side. So this is again a redistribution of charge by induction. There is no touching. Okay, so what I can do, I can connect temporarily or for a very short period to ground and remove some of these electrons. We said ground is a big reservoir of negative charges, so we can remove these extra charges temporarily. Okay, if I do that, okay, and then I break the ground connection, so there is no grounding anymore. Now what do I end up? So notice here, the total charge here is 0. The total charge here is 0. Okay, but now as some electrons have been removed and they went to ground, now the total charge is going to be positive, sorry. So there is a net positive charge, and by breaking ground, now again the total charge here is going to be positive because we have more protons than electrons in the conductor. And now I can remove this, and as I remove it, I end up with a total positive charge on the conductor. So here we basically did two tricks. One is charging by induction, or charge redistribution by induction. Then we touched one side to ground to remove the negative charges. Then we removed the ground and the charged insulator, and we end up with a positively charged conductor. Okay, so here we are combining both charge redistribution by induction and also removing charge by grounding, and we end up with the positively charged conductor. Okay, any question? I hope this is, I know we explained different things, charging an insulator. Usually we charge an insulator by rubbing. It can be positively or negatively charged. A conductor, we can charge it by contacting, okay, with a charged object, but also we can cause charge redistribution in the conductor by bringing it close to a charged object. But that's only temporary charge redistribution. As soon as we remove the charged object away from it, it will go back to the uniform charge distribution of negative and positive charges. Okay. Now, final thing about charging, we go back now to the balloon. Okay, so we charge well, actually the balloon was negatively charged, but let's assume the plastic here or whatever we are charging is positively charged. Okay, and we bring it close to the wall. The wall, let's assume the wall is an insulator, so it does not have free negative charges. So what happens is the molecules or the atoms, the molecules, let's say the molecules, are originally the center of the negative charge, and the positive charge is about the same. So let's say this is a positive charge of the atom, and we have electrons around it. So the center of the charges is at the center of the atom or the molecule. When we bring the positive charge from the balloon close to it, what will happen? The positive charge will attract the negative charges, so the electrons will try to move to one side of the molecule or of the atom, and the positive charge on the other side. So basically, we have what we call the center inside each molecule in the insulator may shift slightly, the center of charge. So here notice that the negative charge is now moving closer to the surface. The positive charge on each molecule is away from the surface. So we end up with a negative charge surface, okay, and we have a positive charge on the plastic here, so they will attract each other. So here, notice that in this case, this is a realignment of the charges in the molecule. Again, so originally the cloud of electrons and the protons in the middle of they have the same center, but as soon as we bring a positively charged object, the electrons, which are negatively charged, they will try to move to one side of the molecule more than the other side. Okay, and so we end up with the negative clouds close to the surface and the positive nuclei away from the surface, and then we will have a force of attraction between the positive charges on the plastic and the negative charges on the wall. So because we said the insulator does not have free charges that are moving freely, so the insulator, you can charge it, but it cannot conduct electricity. All right, so let's check our understanding. Okay, so here we have an insulator A and insulator B. When we bring them close to each other, they will attract. Okay, now we take insulator D and insulator A, so this is another, so we have A, B, and D. We notice that insulator D and insulator A, they repel each other. Okay, the question is, if you bring insulator B and insulator D, what will happen? Okay, will they attract or will they repel? So what I will do, let me, let's use the chat for this one. Okay, what do you think? Will they attract or will they repel if you bring insulator B and insulator D? Okay, so let's give time. All right, so here, all right, so all of the answers will attract. Okay, all right, so let's see. So let's assume insulator A, let's make an assumption. Let's assume it has positive charge. Okay, that means the insulator B, since they are attracting, insulator B must have a negative charge. Okay, now insulator A, we assumed it's positively charged. If insulator D is repelled from it, that means insulator D must have positive charge. So we know D has a positive charge and B has a negative charge, so they will attract each other. Okay, so they will attract each other. Very nice. Okay, so the answers are correct. Now let's make this a little bit more difficult, and let's start the Kahoot. All right, and show this card, and let me go to the Kahoot. Oops. All right, so here, and let's play this. Okay, so please enter your Kahoot and use the pin number that will show. Okay, so please enter your ID number, the full ID number, and if you want to add your name, that's fine. Okay, so waiting for players. Okay, we have 31 attendees, so we give time for everybody to join. Okay, so while the rest are joining, again, the PIN number is 8380413. Remember, I use the Kahoot for attendance, so please make sure you log in, even if you do not answer. Okay, so let me start the question. All right, so now we have a neutral conductor and an insulator A. So the neutral conductor C and the insulator A, they attract each other. Okay? The question is, if you bring insulator D and a neutral conductor C, what will happen? Will they attract or will they repel? Okay? So we have three choices, A, B, or C. So let me give you time to think about it first. So remember, this is now the neutral conductor C is brought close to an insulator D, and we want to find out what will happen. Will it be attracted to it or will they repel? So think about it. I'll give you half a minute. Okay, so let me start the Kahoot. You'll have only 20 seconds to enter your answers. So choose between A, B, or C. Obviously, D is not, there is no D choice in this case. So I will start the Kahoot. Ten seconds. 5 seconds. Okay, so, all right, so we have 18 correct answers and 10 incorrect answers. And so we have maybe 2 or 3 students have not participated. All right, so let's try to reason about this one. Okay, so let me, all right. So this is a neutral conductor and this is an insulator. Okay, now this insulator is charged. What did we assume? Did we assume it's a negative? Well, it doesn't matter. So we said if this is a positive charge, that means this is negative. And so if this is positive, this must be positive. And then we said here, B is negative and D is positive, and they will attract each other. Okay, so we assumed A is positive. So A is positive. Okay, when we bring it to the neutral conductor, what will happen? Okay, so in this case, anybody has, so this is positively charged. Okay, the free electrons will be attracted to this side. So the free electrons will be attracted to this side and there will be attraction. Okay, now we said insulator D, and insulator D has we found it has the same, but doesn't matter. Let's assume this is positive. Okay, same thing. If insulator D is positive, if you bring it to the neutral conductor, the conductor free electrons, the electrons will move. Okay, now what if insulator D was negatively charged? This is just what if. Let's assume this is negatively charged. Okay, so this is an insulator that is negatively charged, and we bring it close to the conductor. Okay, when you bring it close to the conductor, what will happen to the electrons? The electrons will run away, and so the electrons will move away. So they will move on this side, leaving behind a positive charge, and still you have attraction. So both cases, whether this is a negative charge or a positive charge, in both cases, when you bring an insulator, the charged insulator, to a conductor, they will attract. Okay, so you can try this at home. Take, for example, a plastic object, rub it with wool, or and bring it to a Coca-Cola can. Okay, and you will see that the Coca-Cola can, put it on the table so it can roll freely. When you bring a big plastic object that is charged to it, you will see that the can will roll towards the charged object. So there will be attraction, and the attraction is in this case due to the induction or redistribution of charges. The negative charges are moving either, in case of a negative insulator, they will move away from it, and in case of positive, they will move towards it. So in both cases, we have attraction. Okay, So these questions can be a little bit tricky when you have insulators and conductors and charged objects, whether they will attract or will repel each other. All right. So let me stop for a moment and see if you have any questions so far. Yes, they will still attract. So whether whether object D was positively or negatively charged, in all cases, if you bring a charged insulator to a conductor, they will attract. Okay. All right. Any questions? Okay. All right. So I don't see any questions. I hope everything is clear. Now we can move to the next important topic, and this is the topic of Coulomb's law. So this is one of the first law we're going to cover in this course. All right. Okay. Coulomb is a French experiment. Okay. So in this experiment, he has two balls, two spheres, A and B. Okay. And he induced the charges on these spheres, and he wanted to measure the force of repulsion or attraction. Okay. So what he did, he connected one rod that has a charged object here to this fiber. So this is like a torsion pendulum. Okay. So this here can move this way or this way. So let's assume you have a positive charge here and a positive charge here. Okay. He was able to measure the angle. So if this rotates to this position here, so he was able to measure the angle, and by measuring the angle, and this is a torsion pendulum, he knows what is the spring or the torsion spring constant. He was able to determine the force. Okay, and basically he was able to vary the charge. Obviously, he did not vary the charge in a very accurate way. So what he did, he charges one sphere with the charge Q, and he does not know what's the charge Q, and he touches it to another similar sphere. So he knew that this charge Q will be split between the two spheres. When they touch them, this will be Q over 2, and this will be Q over 2. Then he touches this one to another similar sphere, okay, similar conductor. So he knows this charge Q over 2 will be split between the two spheres, and it will become Q over 4, and this one Q over 4, and so on. So he kept doing this. This is how he controlled the charge on the spheres. He really did not have a direct way of measuring the charge, but he could, by touching similar spheres, he was able to split the charge between the spheres. So he would charge the spheres, he would bring them close to each other, and he would measure the angle, and by measuring the angle, he was able to determine the torque, and hence he determined the force. So he was able to determine the force. And he notes the following. Okay, well, let's do this illustration here. Why? Okay, and show, discard, and let's do the experiment, similar experiment to what he did, and try to see what he observed. Copy link, go here, paste. Okay, so let's do the experiment that he did. All right, so here in this simulation we have two charges, A and B. Okay, and we can control the charge on A and B. Okay, so we can also make it positive or negative. We can control the distance between the two charges, and we will be able to get the force. Okay, so let's assume object B, we see here it has 10 minus 4 coulombs. Okay, so that's and here minus 10. The charge here is 10, and here is minus 10, times 10 to the minus 4. Okay, so let's first of all see how the force changes with the charge Q1. So we'll change the charge Q1, and we will see how it changes. So this is the force vector. Here it's 90 newtons. So let's reduce the charge here. Okay, notice the force is smaller. Okay, let's keep reducing the charge. Notice the force is getting smaller, and we're plotting the force here, the force versus Q1. So if we make it even smaller, and so on, so you can see, he notes that the force varies linearly with the charge on one object. Okay, so let's put it back. All right, and let's vary the charge on the other object. So here, let's vary the charge here. Yeah, okay, so here it only allows us to see the when we vary the, but you can see there is a linear relationship between the force that is between the two objects and between the charge. So if you change Q1, the force will change linearly according to that. All right, now let's see how the force changes with distance. Okay, so let's keep the charges are the same, and we'll just vary the distance between the charges. So let's bring it, so here, let me change this, show the force versus R, the distance R. So the distance here is so many meters. So let's bring it close, 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 close. Notice the forces are getting stronger and stronger, stronger, okay? And so you can see how the variation of the force with the distance. So it's actually 1 over R squared. Okay, so 1 over R squared. You can see the plot of the magnitude of the force versus R. It is actually 1 over R squared. Okay, let's try to make the, so here now the forces are forces of attraction between A and B, but if we change the charges to be both positive, so here both positive charges, you can see that these are now forces of repulsion. Okay, and again, the force of repulsion also varies as 1 over R squared. You can see on the top, we can see that the forces are changing as 1 over R squared. So this is basically an illustration of what he observed. He observed that the charge changes linearly, the force, the magnitude of the force changes linearly with the charge and any of the two charges, okay? And he noticed that the magnitude of the force changes as 1 over R squared. And that's how he came up with his Coulomb's law. Okay, so okay, so he found the force is inversely proportional to the square of the distance R between the two spheres, and the force is proportional to the product of the charge Q1 and Q2 on the two particles. Okay, and so he wrote that the force is equal to some constant times Q1 times Q2 divided by the distance squared. Okay, so let's write it ourselves. So let's assume one object has charge Q1, one object has charge Q2. The distance between them are, let's assume they are similar charges, either both positive or both negative. He came up with this equation that the force or the magnitude of the force is equal to a constant K, which is Coulomb's constant, times the magnitude of the charge Q1 times the magnitude of the charge Q2 divided by the distance squared. Okay. Now, in terms of the direction of the force, if the charges are of the same sign, they will repel each other. If they are opposite sign, they will attract each other. Okay. So quantitatively, the constant K, Coulomb's constant, is equal approximately 9 10 to the power 9. It's 8.98 10 to the power 9 Newton meter squared per Coulomb squared. And it happens, we will use also this form, the Coulomb's force is equal 1 over 4 pi epsilon 0, where epsilon 0 is another physics constant, permittivity constant, which is 8.85 10 to the minus 12 Coulomb squared per Newton per meter squared. So please make sure you remember or you memorize these constants, because we will use them a lot. We will use Coulomb constant a lot, and in later chapters we will be also using the epsilon 0, the permittivity constant. Okay, so we can also write this equation in vector form. And so notice here, before I move, so you can see that the magnitude of the force is proportional to the magnitude of Q1. Okay, the magnitude of the force is proportional to Q2, and the magnitude of the force varies as 1 over r squared. So it is a function of 1 over r squared. Okay. Okay. Now, there is a vector form of this equation, but it's a little bit confusing. I just will show it to you for completeness, but I don't advise you to use it because you can easily get confused. All right, so this is the vector form. Let's assume we have Q1 and Q2, and we are interested on the force, the direction of the force F21. So here, this is a vector that extends from particle 1 to particle 2, okay? R12 is a unit vector directed from Q1 towards Q2, all right? And so now we can write this in a vector form. We can write the force on, so this is F12, I should have changed, this should be F21, F21. The force due to object 2, force due to object 2 on object 1. This is the notation that we will use. Okay, so he found that this force is equal to K, which is a constant, times Q1. We did not use now the magnitude, so that it can be positive or negative. Q2 can be positive and negative, times the unit vector R12. Notice R12 is going from Q1 to Q2, and divided by the distance squared. Okay, so let's take a couple of examples. Let's assume Q1 is positive and Q2 is positive. Okay, and let's verify this. Okay, so if this is positive and this is positive, their product is positive. Okay, so this is positive, this is positive. Okay, and R12 is pointing in this direction. Okay, no, so this, yeah, okay. So if this is positive and positive times, so no, actually this was correct. This was correct, sorry. So this is F12. We're determining the force on object 2. Yeah, okay, so I want to make sure. So here the forces are forces of repulsion. So normally we should find if these two are of the same sign, the vector here will be in the same direction as the r vector, which is correct. So here this is positive, this is positive. Okay, R12 is pointing to the right, and F12 is also pointing to the right. Same thing if we have Q1 and Q2 negative. So if Q1 and Q2 are negative, so negative times negative will give us positive. So let's assume here the two forces, the two charges are negative. There will still be a force of repulsion. So F12 is still going to be equal to a positive, because negative times negative will give us positive. This will be positive. It will be in the same direction as the unit vector R12. Now let's take one positive and one negative. All right, so if we take one positive, let's assume Q1 is positive and Q2 is negative. In this case, the forces will be forces of attraction. So this will be F12, and this will be F21. Okay, and so we can see F12 in this case has the opposite direction of R12, and so if you multiply the positive times the negative, this will be negative, and so we can see that this vector is the opposite direction of R12. You can see this can be quite confusing, and that's why I do not suggest you use the vector form of this equation, because you can easily get confused with the subscript and so on. So I would recommend that you only use the magnitude form, which is K, Q1, Q2 divided by R squared. Okay, once you find the magnitude, then you can use your reasoning to determine what's the direction of the force. So for example, in this case, if Q1 and Q2 are the same sign, both of them are positive. If I took, this is my positive axis, x-axis, okay, I have determined F12, I have determined F12, the magnitude of F12. Now I can write F12 in a vector form. I can write F12 is just equal to K, Q1, Q2 divided by R squared times I. Okay, so basically, first of all, determine the magnitude of the force, then determine the direction using the reasoning. Similar charges repel each other and opposite charges attract each other. All right, please avoid the vector. It's confusing for me, so I don't like to use the vector form. All right, okay. So the direction of the force is automatically obtained from the sign and of this vector equation, but the vector equation can be difficult to, you can easily make a mistake. All right, so again, always remember, so if you choose your positive axis, so you can determine, this is your X and Y axis, you can determine that this is a positive force, this is a negative force, and if the same thing, if both of them are negative, if they are opposite charges, and you choose, for example, your, again, X-axis and Y-axis, so this force is negative and this force is positive. Okay, now I want quickly, this is comparison between the electrostatic force and the gravitational force. So this is Coulomb's equation, okay? Newton's equation for gravitation force, unfortunately, you did not study it in physics 121. It's this one. If you have any objects of mass m1 and m2, and let's assume these objects are in space, in free space, okay? If you bring them close to each other, they will attract each other with a gravitational force that is equal capital G. This is a gravitational constant, which is 6.67 10 to the minus 11 Newton meter squared per kilogram squared, times the mass of object 1 times the mass of object 2 divided by R squared. So not the similarity between M1 and 2, R squared in the denominator, R squared, and here we have a Coulomb's constant, here we have a gravitational constant G. Okay, now you might ask me, well, when we study, we said F is just equal to mg. So how come you're giving us a different equation? Well, it happens that this G here, so let's take the Earth, let's assume the mass of the Earth. We know the mass of the Earth, and we have an object on Earth that has a mass m, okay? And let's assume we know the radius of the Earth, RE, okay? You can write the gravitational force is capital G, the mass of the Earth, times the mass of the object, divided by the radius of the Earth squared. This here is equal to G times m. So actually, the gravitational, the G is just equal, and on Earth at least, is equal to the mass of the Earth times the gravitational constant G, which is 6.67 10 minus 11, divided by the radius of the Earth squared. So if you are on the moon, this is on the Earth. If you are on the moon, you can also determine what is the gravitational the value of G on the moon. It's going to be the mass of the moon times the gravitational constant G divided by the radius of the moon squared. Okay, so unfortunately you did not cover this chapter because well, I don't know why. I think it's a very important chapter, and it explains how the universe is held together. The gravitational force is what keeps the planets around the sun, the moons in their galaxy, and so on. Okay, so these two equations are very similar, except we know Coulomb force can be a force of attraction or repulsion. So this can be attraction or repulsion, but the gravitation force is always a force of attraction. So this is the big difference between them. We have never seen a gravitational force of repulsion. Okay, I hope this is clear. I know this is something you did not cover before, gravitational force, but this is the in a very short explanation of the gravitational force. Okay, so we can say the electrostatic force has the same form as the gravitational force, but unlike the attraction of gravitational force, electrostatic force can only be, or can be repulsion or attraction. All right, Any questions? I want to make sure if you have any question, please stop me or raise your question. Okay. All right, let's see if we can do an example here. Okay, let's take the hydrogen atom, okay, and let's try to compare the electrostatic force and the gravitation force. So we will take a very simple model. We have a proton in the hydrogen atom, and we have an electron. So this is a proton, and this is an electron. And we will assume the distance between them, the average distance is 5.3 10 to the minus 11 meters. Okay, and we want to calculate the gravitational force and the Coulomb force. We know the mass of the proton. We said it's 1.67 10 to the minus 27. The mass of the electron is 9.11, I think, 10 to the minus 31 kilograms. Okay, so we can determine the gravitational force in this case. So gravitational force is capital G times the mass of the proton times the mass of the electron divided by the distance. So let's call this R squared. Okay, so we will replace the numbers later on to find the values. Okay, the electrostatic force is going to be Coulomb's constant times the charge of the electron, which is E, times the charge of the proton. So this is minus E for the electron, and for the proton it's plus E, but we're doing the absolute value divided by R squared. All right, so this is the two simple equations, and we just need to replace the numbers and determine the values, and that's what we have done in the next slide. Okay, so here this is the electrostatic force. So gravitational, the Coulomb constant is 9 10 to the power 9. The charge is 1.6 10 to the minus 19. It's squared because the charge of the electron is minus 1.6 10 to the minus 19, and that of the proton is plus 1.6 10 to the minus 19, divided by the distance squared. And we know that Coulomb force is 8.2 10 to the minus 8 newtons. Okay, let's see what's the gravitational force. Okay, so the same equation as we've seen earlier. G is 6.67 10 to the minus 11. This is a gravitational constant. This is the mass of the electron, and this is the mass of the proton, and this is the distance squared between them. Okay, we find in this case the force is 3.6 10 to the minus 47 newtons. Notice it's negligible. It's really insignificant compared to this force. This one is almost 10 to the minus 7 Newton, and this one is 10 to minus 47 Newton. So clearly, when you go to the atom scale and nuclear scale, the gravitational forces become insignificant compared to the electrostatic forces. That's why in many problems, when we deal with electrons and protons, we usually neglect gravitational force. So when you don't have to worry about the gravitational force in that case, because it's really non-significant compared to the electrostatic force, the force of attraction or repulsion between the charges of the particles. But if you go to larger objects where the masses become significant, then you cannot just ignore, for example, the Millikan experiment where he did the water drops. He had the electrostatic force in one direction, gravitational force in the other direction, and when they balanced each other, he was able to determine the charges. So in this case, he could not ignore the gravitational force on the drop of water of oil, because it's not insignificant. But for electrons and protons, so if you take the ratio, the electrostatic force divided by the gravitational force is 5.3 10 to the power 39. So the gravitational force is really insignificant in this case. Okay, now this is the convention for notation in survey. Unfortunately, it's not a uniform convention. Halliday and Resnick has the opposite convention. This is why I still get confused, because I used to teach from Halliday and Resnick, and now I'm teaching from Survey. And so the force has two subscripts. The first one indicates the due to charge of particle. So the 5 means this is the force due. Let's say this is charge particle 5. This is particle 4. When we are doing the force on 4 due to 5, we write 5 first. And that's why I still get confused. All right. And the second subscript is what is the on which charge. So this is now, for example, force due to 5 on 4. Okay. So this is the convention that we will use. So for example, here we have charge Q1 and Q2. If I ask you F21, that means the charge, the force due to charge 2 on charge 1. And if I ask you F12, obviously you can see these are two forces in opposite direction. So you cannot say they are equal. They are equal in magnitude, but opposite in direction. F12 is the force due to particle 1 on particle 2. So this is the F12. All right. So correct me when I get confused, because it's difficult to get rid of habits, and because I'm used to the opposite, just exactly the opposite convention. Okay. Now another important principle of these forces, they add. There is a superposition principle, and it's actually the same as gravitational forces. In gravitational forces, if you have M1, M2, and M3, okay, you can determine the force due to 1, due to 2. So this is force due to mass 1 on 2. Yes, and you can determine also the gravitational force of attraction, F, let's call this 3, due to 3 on 2. And then you can add the two vectors. You do the vector addition and you add them. Okay, so there is superposition for gravitation force, but also we have superposition for electrostatic force. So in this case, you have 4 charges, okay, and we are interested in determining the total force on Q1. So what we can do, we can determine the force due to Q3, the force due to Q2, the force due to Q4, and we add them, vector addition. So let me do it. So let's assume Q2 and Q1, they repel each other, so they have the same charges. Okay, let's assume, so this is the line that joins. Let's assume there is a force of attraction between 3 and 1, so there is another force of attraction here, F1, 3, okay. And for Q4, this is also a force of repulsion, so this is F due to 1 on 4. Okay, so now we have determined all the forces that are acting on charge Q1, and we can add them. If we have these forces in unit vector notation, we can add the x components together times I, we add the y components together times j, and we add the z components together times k. Or we can do it graphically. And remember, graphically, we can just draw this graphically. Let me show you, remind you how we can do it graphically. Okay. So the net force is equal to the sum of the forces. This is a vector addition. It's not a scalar addition. Okay. So we can draw them. So if you draw the parallel to this vector, and then you can join this here. So this is the sum of F31 and F41. Okay. So this is the sum of these two vectors. Okay. Now I can draw the parallel to this and add to this vector, and I can now get the other. Oops, oh, I lost my pen. Okay, all right. So here, this is the net force. So if you have a diagram of the forces, you can add them graphically. And if you have the unit vector notation, you can add these vectors by adding the components of the vectors, x components separated from the y components and the z components. Okay, so this is what we call the principle of superposition. The net force acting on any particle is a vector sum of the force acting on this particle due to each of the other individual particles. Okay, So you might have a problem where you have 2 or 3 or 4 charges. You have to just consider each charge separately, determine the magnitude and direction, and then solve. All right, so let me go back to the Kahoot, and I want to ask this question. Hopefully you did not leave the Kahoot. All right, so this is the Kahoot. Okay, so let's go to the next question. All right, so here the highest score is by 59177. Okay, the next question is the following. All right, so read the question, and you have only 3 choices, A, B, or C. Please, you have 30 seconds to answer. Okay, so choose between, so here we are interested on the net electrostatic force on the central proton. So we have an electron to the left, proton in the center, and a proton to the right, and we want to determine what is the net force, electrostatic force on the proton. Okay, so make your choice. Okay, so you still have 20 seconds. 10. Okay, so let's look at the answers. All right, so we have 22 correct answers, but 5 incorrect answers. All right, so let's look at this. Okay, it looks like, make sure my pen, no, I lost my pen. It's not writing anymore. Okay, and usually when that happens, I have to turn off my computer and on again, but I will not, I don't have time to do that. So I will just go. So clearly, we have between the proton and the proton, there is a force of repulsion. So the force is to the left from the proton on the right. The force of between the electron and the proton are forces of attraction because these are opposite charges. And so it's also a force to the left. So the total electrostatic force can only be to the left. All right. So this is what we are doing here. Okay. So let me see. We go to presentation mode. Okay. So, all right. So here is another example. Okay. So in this case, we have 3 charges, Q1, Q2, and Q3. And we are given the charges. Q1 and Q3 are equal 5 microcoulombs, and Q2 is -2 microcoulomb. And the distance A is 1 meter. And find the resultant force exerted on Q3. Okay. Because my pen is not writing anymore, I will just go. So basically, in this case, we have to do one force at a time. So we know Q1 and Q3 will repel each other. So there will be a force along, let me see if I use my mouse. If I use my mouse, okay, so we will have a force like this. This is a force of repulsion. This is F on due to 1 on 3, okay, and we have Q2 is negative, so this force is like this. Okay, so this is F on from 2 on 3, and so we determine the magnitude of these forces. And since we have also the angle, this angle is 45 degrees. Okay, so we can write this force in unit vector notation. So once we determine the magnitude F13, we can write times cosine 45 degrees I, and we also multiply the magnitude times sine of 45 j, because it has x, positive x and positive j components. The force F23, once we determine the magnitude, it will be negative. And so let me directly go to the solution, the next slide. Next. All right. So here we determine the magnitude F13, we just applied Coulomb's law. We determined F23, okay? So we find one is 8.99 newtons, the other one is 11.2 newtons. So for F13, we multiply by cosine 45 to find the x component. And so this is the x component, and the y component is the same, 7.94 times 11.2 times sin 45. So now we have the x component and the y component. For F23, it's in the negative x direction. So if we want to determine the sum of the vectors, so this is 7.94, this is the x component, plus minus 899, this will give you minus 1.04. And if we add the y components, the y component for one force is 0, the other one is 7.94, and then we can write in unit vector notation. So we can determine the magnitude and the direction. Okay. If I want to determine the angle theta, I can see that. So let me draw the resultant force. So the resultant force. So let me draw this here and this here. So the resultant force will be something like this. Sorry, I'm using my mouse. Okay, so it should be straight. Okay, and so this will be the angle theta, and you can do the inverse tangent of the y component divided by the x component, and you have to make sure that it's more than 90 degrees. So I will stop here. Any questions? Sorry for taking 1 minute longer. Okay, so I will see you next week in class, hopefully. So we will see each other. We will have a chance to also introduce each one of you to introduce yourself, and we will proceed. Okay, have a good weekend, everybody. And so remember, you have to go over the material in the textbook, and we will not. We will probably have. I will post homework next week. So because we did not cover enough material yet in this chapter. So I will see you next week.